Hi, today we want to discuss valence bond theory. In today's video we're going to discuss valence bond theory. We're going to do 3 examples where we use valence bond theory to describe bonding in a molecule, and in the process we're going to define and discuss sigma bonding. So let's start our discussion today thinking about the very simple molecule dihydrogen. We have a hydrogen that's going to bond to another hydrogen. We'll label these hydrogens hydrogen A and hydrogen B to keep them straight. And the idea is that each of these hydrogens has an atomic orbital, 1s, and it's half filled, right? Each of these hydrogens has a 1s1 configuration, and these orbitals here are 1s orbitals. The idea behind valence bond theory is that we're going to take these two half-filled orbitals, right? So here's 2 half-filled orbitals. We're going to combine them and we're going to make a chemical bond. Okay, atomic orbitals. And as we do that, we'll need one of these electrons to spin pair, in other words, change spins. And what we'll do is we'll make a filled orbital where we have now combined these 2 electrons. So again, the big picture idea behind valence bond theory is we're going to form chemical bonds by overlapping half-filled atomic orbitals. When we make a combination like this, we take one s orbital and another s orbital, say, and combine it together. You can imagine what that might look like. So if I have a 1s orbital on one of my hydrogens, hydrogen A, and I have a 1s orbital over here on hydrogen B, well, when I combine them together to make the molecule, I'm going to form some kind of overlapped orbital that combines the 1s on one of the hydrogens with the 1s on the other hydrogen. And so it looks like this. Here's one of my protons here. There's another proton. And here's my chemical bond axis that runs through something like this. This bond here is called a sigma bond. It's called a sigma bond, and what differentiates it, what sets it apart, is as we rotate this bond about the internuclear bond axis here. So imagine spinning it around in this direction. The bond has symmetry with respect to rotation. We can also imagine and describe the bonding in F2 using valence bond theory. F2 again is another homonuclear diatomic. We have 2 fluorine atoms, fluorine A, fluorine B. Each one of these has an electron configuration of helium 2s2, 2p5. If we distribute those electrons into the box diagram mode, we can see that we'll have here's my 2s, here's my 2p. Let's say this is for fluorine A. Fluorine B, I'm going to have exactly the same configuration here. I'm going to have the 2s orbital here and the 2p orbital here. If I actually distribute my electrons in these boxes, I'll have 2 electrons in the 2s. Just notice I was missing the 2 there. And I'll put my 5 electrons in here. And I do the same thing for fluorine B. The big thing that I notice is that I have a half-filled 2p orbital on fluorine A and fluorine B. So I can describe the bonding in fluorine by thinking about a half-filled orbital on fluorine A, a 2p orbital, overlapping with a half-filled atomic orbital on fluorine B. And if we were to sketch that interaction, we would see that it is also a sigma bond. So if we again kind of just imagine our Cartesian coordinates here, if this is my x direction here and my z directions here, and let's imagine my y direction comes through something like this. If I draw my 2px orbital, let's say, and it goes along in this direction, like this. So this is my 2px orbital. I can overlap a 2px with a 2px, and that interaction would look something like this. So here's one of them, and what I'll do is I'll overlap the other one so that the regions of similar shading overlap. And we'll see here as we draw the kind of a dashed line through the bond axis that this bond is also a sigma bond, because as I rotate about this bond axis here, the bond is symmetrical. So this is another sigma bond. If we go and do our last example, and in this case we have a hydrogen and a fluorine, and we know that we're going to overlap because we have a chemical bond forming. Our hydrogen, obviously, we just have a 1s1 configuration here, and here we have our fluorine has the same thing that we talked about before, as a 2s, and here's my 2p orbitals. 1, 2, 3, 4, 5, 6, 7 valence electrons. You can see the half-filled orbitals that are going to overlap the 1s on the hydrogen with the 2p on the fluorine. And so again, you can kind of imagine what this interaction will look like. Here I have the, say, 2px again. I'm going to have something like this. I'm going to take this orbital on the fluorine, and I'm going to overlap with this orbital, 1s orbital on the hydrogen. So let's say I'm going to draw it over here. And again, regions of similar shading overlap. And you can see that this interaction, switch to red this time for the internuclear axis, this bond would also be a sigma bond because it is also symmetrical with respect to rotation about the bond axis. So we can see that valence bond theory adequately describes the bonding in these three case studies that we've done, F2, HF, and dihydrogen. So today we discussed valence bond theory. We said that covalent bonds are formed by overlapping half-filled atomic orbitals. We showed 3 examples showing how the method is very useful. We also discussed sigma bonds, and we said that sigma bonds are those bonds which are symmetrical with respect to bond rotation. In our next video, we're going to continue building upon what we've done in this video, and we'll discuss more complex scenarios. But thanks for watching, and I hope you have a good rest of your day.